Bam! Mr. Tarrou. In this lesson, we are going to define and learn something called function notation. Through this lesson, we're going to do a word problem application where we set it up and evaluate this function at a particular value, and then finish up with two more examples where we just learn how to substitute either a number or an expression into a function, looking at or just given the function notation format. Okay, so what is a function notation, or what is function notation? Well, function notation allows you to name a function and identify, it's a little bit covered up here, actually completely covered up, but identify the independent variable. Okay, well, an independent variable is, in a real life application like what we're dealing with here, is a variable that you have some control over. It is also called the input value. A dependent variable is what you get out of a function, or just the answer that you get from an equation. Okay, so function notation allows you to name a function. Name a function. Yeah, name a function like me. You're not going to, my students don't go, hey, teach, hey, you, dude, man, whatever. I have a name. It's Mr. Tarrou. So that's all function notation is as far as equations are concerned. And why do we want to know or understand or use function notation? There's many reasons. The two of them I'm going to deal with in this lesson. Here, we got y is equal to 35x plus 400. Well, we have all these exponents of 1, and that means that we're looking at a linear function. And by the way, I'm going to be saying the word function all through this lesson. Let's not forget there's relations and then there's functions. A relation is basically a situation where an x value or domain value can be mapped up or paired with one or more y values or one or more range values, whereas in a function, every x can only be paired up with only one y. Every domain value can be paired up with only one range value. And I have a lesson, we just talked about it earlier. I'll put a link in this lesson as well if you want to go back and review the difference between relations and functions to further your understanding if you need to. And my students do need to, because we've already covered it in our class. Okay, so we have y is equal to 35x plus 400. This linear function is been graphed, and the hard part about teaching the beginning of any class is there's so much that you don't know, and especially with you, all my YouTube viewers or students, I don't know if you've graphed linear functions or not, and the part of this video is really not teaching how to graph a linear function, but let me just run through it quickly, and again, I'll put a link here or here, somewhere at the bottom of my lesson, so you can skip to another video and learn how or review how to graph linear functions if that's something that you need. We have a y-intercept of 400 and a slope, that's the number that's in front of the x, the m, is rise over run. So we're going to, from 400, our y-intercept, the number that's off by itself with no variable attached to it, we're going to go up 35 and over 1, up 35 and over 1, up 35 and over 1. Draw a few dots and draw a line through those points, and that is going to be a line, again, because these exponents are equal to 1. So I have this linear function graphed. Great. It doesn't mean anything. Nobody talks in terms of x's and y's outside of a math class. So that's why people never think they ever use algebra again once they get out of school. Well, you do, in some form. And if you don't, well, one thing, again, we don't talk in terms of x's and y's, and there'll be some applications, or not applications, but concepts that you learn in algebra that you really won't use outside of a math class unless you're in a field, specifically heavy in mathematics. But you will use the logic, the logic skills to work your way through complex problems, those problem-solving skills where you go, okay, I need to do this first, and then I can, okay, so I can't, I got 5 steps I need to do. I can't do the 4th step first because that's not going to really work out with the way, logically the process that we need to go through. And you do see that a lot in mathematics. There's plenty of stuff in math where you have these really complex situations that you have to realize that there's a particular logical sequence of steps you need to work through to finish the problem or solve the problem. Well, there's a lot of real-life applications. I don't know, framing a picture. What do you need to do? How do you need to get the wood? How do you need to cut it? How are you going to attach the corners together? Logical steps you need to work through to get that problem solved, to get that frame built. Okay, so one purpose of function notation is to give a function a name, give it some context. That graph meant nothing, just a bunch of x's and y's. You'll see some context to it once we finish working through our word problem. Another reason we want to use function notation is, again, that name. You don't want to call everyone, hey, you, dude, thing, whatever. So we've got what looks like a cubic function, and if you haven't studied cubic functions yet, don't worry, my students haven't either, unless they had a little taste of it in pre-algebra, which I kind of doubt. But we have a cubic function here drawn in blue. It's named function f, and the independent variable is x. We have a orange line that kind of goes down to the left and goes down to the right. It looks like a parabola, if you've studied that yet, and it's going to be called function g. And then we have a straight line in green, excuse me, and that's function h. Well, there's a lot of real-life application, a lot of problems that you learn in algebra in every class from there on out, where you need to find out where two graphs cross, intersect. Well, there's a lot of stuff going on. There's an intersection point here, 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 and here. But if I say, where does function h and function f intersect, there's only one intersection point. So if I say solve or find where function f and function h intersect, then you know exactly what two lines or curves on this graph that we're talking about. And you can see there's only one intersection point. So just by saying where does f and h intersect, you know exactly where to go and either work out by hand or solve this graphically with your calculator. Again, another reason why we'd want to name our functions so that in very complex situations we can see or know what graphs we're talking about. Okay, let's get this back up here. Stay. Example, you hire a painter to paint the exterior of your home. The supplies will cost $400, and then he's telling you, or she's telling you, that it's going to be $35 labor after that. Write a function for the cost of getting your home painted. Write a function for the cost, and it's a function because it's not like, you know, if it takes 10 hours to do the job, then there's one specific price you're going to have to pay. You don't it's not one of two different prices or more different prices. For every x, there's going to be one y value. So write a function for the cost. Okay, write a function for the cost. I want an equation that is going to tell me how much it's going to cost to get my house painted. Okay, so cost is going to be equal to something. So it's sort of like my function name is cost. I'm going to do a bunch of calculation, and when I'm done, that's how much it's going to cost. Now, okay, independent and dependent variable. We talked about that in an earlier lesson. You hire a painter to paint the exterior of your home. The supplies will cost $400. And then from there, the labor. Now, labor is meaning that's how much you're going to have to pay for the hours that they work. If they work 1 hour, you're going to pay $35 in labor. If they work 2 hours, that's going to be 35 plus 35. I'm running out of room there. If it's 3 hours of labor and they charge 35 per hour, that means that they're charging you $35 for every one hour. Let's see, then that would be $35 for the first hour, $35 for the second, and another $35 for the third. So every time they work another hour, you're paying another $35. So what's the independent variable? Because this problem says that we have something about, well, there's a lot of stuff here, but hire a painter, exterior home, the supplies will, the word cost is $400, and then there's some additional cost based on labor. Well, the cost is going to depend on how long it takes them to do the job, right? So the cost is the dependent variable. As you can see, I have it written over here to the left alone, kind of, to the left of the equal sign. And the hours, that's a variable. I don't know if it's going to take them 1, 2, 3, 4, 5 hours to do the job. So it seems like the hours are going to determine how much the job costs. And, well, it's going to cost $400 for the supplies, probably just the paint as well, and then after that, the labor is $35 an hour. So no matter how long they work, there's going to be $400 of cost just for the supplies. And then it's just a matter of, with the 400, do you add 35 once for 1 hour, or do you add 35 twice because they worked for 2 hours, or do you add 35 another 3 times because they worked for 3 hours? Well, what if they worked for 5 hours? Are you really going to write 35 plus 35 plus 35 plus 35 plus 35? Or are you going to just start going, come on, you know, it's 35 times 5. It's 35 times 4. It's 35 times 3. It's 35 times the number of hours the job takes. So the cost of the job is going to be determined by, chalk down, how many times I'm going to drop this in the video, is determined by the number of hours that the painter takes to do the job. So the cost in hours is equal to 400, that one-time purchase for all of the supplies. You don't want to buy like half the paint and then realize they ran out and go back and buy another half the paint. Half your house is going to be a different color, right? So there's a one-time purchase for the supplies plus $35 for every additional hour this job takes. And this is your function. It's not y is equal to something blah, 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 x. This is plain language. Everyone talks like this. I have a job. It's going to cost me $400 plus $35 for every hour it takes the painter to do the job. Calculate the cost if the job takes 30 hours. Okay. Well, how much is going to be the cost if it takes 30 hours? Well, 30 is the hours. 30 is the number, the value, the independent variable, the input value. And again, that 400 is that one-time charge of the supplies. And also when you read these word problems and you're trying to set up the equation to model that real-world setting, the number that you realize is going to repeat, and that per hour is a rate notation, that $35 for every 1 hour, that also, that word per gives you a hint as to what number in the word problem is going to be the one that repeats based on some kind of, well, variable. And so we have 400 plus 35 times 30. Now when you get all that typed into your calculator correctly, the 30 times 35 is going to be 1,050. And when you add 400 plus 1,050, you get $1,450. And let me double check. Yes, that is how much the job is going to cost this particular homeowner if they hire this painter that's saying the supplies, the paint's going to cost $400, and they're charging you, again, $35 an hour. No. Alrighty then, I totally forgot to put my graph into context. Do you see what is going on with this graph on the green board and what we did with our application problems? Oh, which by the way, you can see I changed a little bit. I wrote out the number of hours of 0, 1, 2, and 3. I did it verbally, but I didn't like the way it visually looked. And I'm figuring out the cost of, well, if I don't end up hiring the painter, but he has already bought all the supplies and worked 0 hours, it's going to cost me $400. If he takes 1 hour to paint the entire house, which I'm sure is not going to be the case, that's 400 plus 35. For 2 hours, you're adding that 35 twice. For 3 hours, you're adding that 35 3 times. And if the numbers are simple enough for you to, you know, this is sort of like a pattern recognition type setting. Even if the numbers are simple enough that you can just sort of like rattle those numbers right off the top of your head, like maybe he was only charging $10 an hour and you were like, oh, it's $10, $20, $30, $40, $50 an hour for, or $30 or $40 for labor. Slow down and let your brain sort of think about how are you getting your answer? Oh, I'm just repeatedly adding by, in this case, 35. So it must be 35 times, again, the number of hours, and just giving you a different look to the same problem. Well, that function notation, that sort of function name, and then the parentheses, the independent variable on the inside, this is my f of x, my cost per hours. This is my y. All right? And then we have 400, which was my y-intercept. And then we have 35 times the number of hours. So this is a graph of this function with no real-life context. Well, now that we realize that this equation is supposed to be describing how much it costs to have a home painted, well, it wouldn't make any sense to include any numerical values for x, which is negative, because that's not possible in this real-life setting. And also, now that we have some kind of real-life concept or context to this problem, oh, and you're not going to have any negative values for the cost of the job, now we can say, well, x is not just x, it is the hours or the time to complete the job in hours, and this y-axis is the cost to do the job in dollars. Okay, so now we have some real-life meaning to this general equation, this generic equation, and this graph. Okay, so getting this out of our way, our last two examples are, if f of x is equal to 2x minus 3x plus 1, evaluate, I think this can be the most I've ever dropped any chalk in a lesson. Okay, chalk down. Let's just leave it down there. I keep dropping it, right? If f of x is equal to 2x minus 3x plus 1, evaluate f of 2. These particular problems or notation for function notation, very few students struggle with because it's just a number that they're plugging in for x. You see where we have the same function name of f, but inside the parentheses is a 2 instead of an x. I took out the x and replaced it with 2. So in my, actually, let me change this a little bit, because I just thought of a mistake that my students make all the time. Let's make that f of negative 2. Well, first of all, you see what I did with my notation again? I took out the x, replaced it with negative 2. So a variable is just an empty spot to put an unknown value. So we have 2 parentheses squared minus 3 parentheses plus 1. I'm not even looking at what's inside the function notation. I'm not even looking at what my value is for my independent variable, my input variable. I'm just writing parentheses. And now I'm going to say, oh, wait a minute. Okay, yes. Everywhere that there was an x, I put a set of parentheses, and now there's a negative 2. So that's what I'm going to do. I'm going to put in negative 2. And now let's simplify or evaluate this expression, and this is going to be my way. So let me put b up here. Okay, there is a difference between negative 2 squared and negative 2 squared. Now this number is small enough, you could probably do it in your head. I hope so. And maybe if you did not include the parentheses or write them correctly, you would still get a correct answer. But if you had a complicated number like a decimal or something like that, and you were using a calculator to help you, the syntax does matter. And you should understand that these two expressions do give you a different answer. This negative 2 to the second power is negative with the 2 being squared, and really with that negative not inside the parentheses, not being affected by that exponent of 2, it's really kind of like a negative 1 times 2, which is going to give you an answer of negative 4. Whereas if you wrap it in parentheses, like it is in your function notation here, negative 2 squared is going to be negative 2 times negative 2, and when you multiply two negative numbers together, you get a positive answer. That's why I wanted to change that sign on our 2 here in our example. So we have, well, please excuse my dear Aunt Sally. Please, parentheses, excuse, exponents, multiplication and division, which are together really as far as how you do them. left to right. We have an exponent here, and then Aunt Susie's addition and subtraction. We have negative 2 times itself, negative 2 squared. So negative 2 times negative 2 is positive 4. Well, let's go ahead and do this. We have, well, let's do one thing at a time. Negative 3 times negative 2 plus 1. Okay, now we're going to do please. There was no really parentheses to speak of because these just have single one term in each side of them, just a number. Excuse exponents, just took care of that. Please excuse my dear, multiplication and division. Well, we have some multiplication to do. It's multiplication, division. It's whatever comes first as you read left to right. So 2 times 4 is 8, and negative 3 times negative 2 is positive 6 plus 1. And then Aunt Sally, just your order of operations, add and subtract. You don't add before you subtract. Add and subtract are sort of like on the equal playing field. You read your problem left to right and you do whatever comes first. Well, again, that was actually another issue I wanted to bring up, but because I changed the negative 2 to, or positive 2 to negative, I've avoided that one because this was negative and that was positive. 8 plus 6 is going to be 14, and then 14 plus 1 is 15. And my final answer is f of negative 2 is equal to positive 15. Now I changed my example, so let me just double check. Okay. If I had, let me go back because I do want to just point this out if anyone has struggles with order of operations. If I had left that positive 2, well, positive 2 times itself, 2 times 2 is still going to be 4, and negative 3 times 2 is going to be negative 6. Now, when you look at here, and you think of, please excuse my dear Aunt Sally, and you go, Aunt Sally, addition, subtraction, oh, I got to add before I subtract. So you look at just that piece, and you do 6 plus 1 is equal to 7, you're going to get a wrong answer. You want to do your addition and subtraction and your multiplication and division. You don't multiply before you divide. You don't add before you subtract. They're in equal level playing field. You read your problem left to right and you do whatever comes first. So 8 minus 6 is going to be equal to 2. And then 2 plus 1 is going to be equal to 3. But of course this is a different answer because, well, now I'm using positive 2 instead of negative 2. And okay, so our final answer is in this format with a positive 2. 3. If I wanted to write this as a coordinate, this was my input or my independent variable, this is my output or my dependent variable, that written as a coordinate would be 2, 3, if just in case you need that. And our final example of our lesson is f of x plus 3. Now this is an expression with two terms. They're separated by addition and subtraction. That students will struggle with a little bit even if they do the two kind of really automatically. So again, when you have function notation and you're being given something to substitute into the function, I like to just don't even pay attention to what you're plugging in. It's function f of something. Well, function f is 2 times something squared minus 3 times something plus 1. Just write the function out with a blank space everywhere there's a variable. And then go, well, that looks great, or that looks a little weird because it's kind of like a whole expression just instead of just a regular little number, but it's okay. You know there's an empty space that's being squared and another empty space next to the negative 3. And then in that empty space, we're plugging in x plus 3. So we're going to have 2 times x plus 3 times x plus 3 minus 3 times x plus 3 plus 1. I'm just writing that x plus 3 out twice because there is an exponent of 2. We're going to distribute these binomials together. And we're also going to distribute through that negative 3. And we have 2 times, now all this stuff going on here, x times x is x squared, and x times 3 is 3x. And then that first term in the first grouping just got multiplied to every term in our second grouping, so move on to the next term. Positive 3 times x is positive 3x. And positive 3 times positive 3 is 9. I'm going to close up the parentheses because now there's a minus sign in a new grouping. Negative 3 times positive 1x. And you can put coefficients of 1 in here if you like. Negative 3 times positive 1 is negative 3x. Negative 3 times positive 3 is negative 9. Okay, so I've also distributed through that parentheses right there. And now we're going to add, let's see here, like terms. Terms that have the same variable and the same number of those variables. Well, these two terms both have x's, and they both each have just 1x. So these are like terms. So we have 2 times 1x squared. 3 plus 3 is 6x plus 9. Minus 3x, negative 9 plus 1. We're combining terms or combining numbers that have different signs, so we're going to subtract those numbers and keep the sign of the largest absolute value, or kind of like, 9's bigger than 1, 9's negative, so the answer is going to be negative. This comes out to be negative 8. We're now going to distribute this positive 2 through the parentheses. 2 times 1 is 2x squared. 2 times 6 is 12. 2 times 9 is 18. And minus 3x minus 8. And now we have a like term. Let's see here. We have an x to the first here and an x to the first there. We're going to combine those like terms of positive 12 and negative 3x. Where it's going to give us 2x squared. 12 minus 3 is 9. And then we have positive 18x and negative 8. Well, 18 minus 8 is equal to 10. And this is f of x plus 3. Let me double check. Make sure that I haven't made some kind of silly mistake. And it matches my notes, and that is the end of my last example. And that is, well, it's gone now, but that is how you work with function notation. I'm Mr. Tarrou. Bam! Go do your homework.